Welcome to Calculus AB video for Skill 119. I can apply limit laws and use this to find limits algebraically. And featured to the right is an ionic column, and the trivia question for the day is: the grooves carved into the column have a word there's a word to describe that. What is the word to describe the grooves carved into the column? Alright, now that we've explored limits graphically, what we're going to do is we're going to start to look at limits algebraically. And when we were looking at limits graphically, one of the things we noticed is basically some of the time the limit as x approached a of f of x just meant f of a, i.e. what is the y coordinate of that curve. There's a what is the y coordinate, and that's your limit. That sort of direct substitution is useful, but it doesn't always work. As we saw occasionally, sometimes we had a left-hand limit which did not agree with a right-hand limit, and so that substitution didn't work. So what we're going to do today is we're going to look at some algebraic laws and explore options that we have to solve problems where direct substitution doesn't work. And it generally is pretty clear when direct substitution will work and won't work. So the first thing I've done is I've listed some properties of limits that we should know. And the preface is, if you know the limit of one function is L and the limit of the other function is M, then we could say the sum rule is if you take the limit of the two of them added together, that is equal to the limit of the first plus the limit of the second. Similarly, if we take the limit of the first minus the second, that is the same thing as taking the limit of the first minus the limit of the second. Our product rule, you're taking the limit of the first times the limit of the second. Our quotient is the limit of the first divided by the limit of the second. And all these kind of make intuitive sense. This one has a little caveat. This won't work if the limit of your denominator is 0. So we need to be careful, and that's one of those conditions where algebraic laws really come into effect for us. One other thing we have is the limit of when we have a constant being multiplied by a function, we could actually move the constant out in front and take the limit of the function itself. So that's how we get that k times m. These are summarized in the reading in the textbook, so you can check those out too. There's one more limit law, which we'll see on the next page. And that limit law is the power rule. So if you raise a function to a power, and you want to take the limit of that it will equal just your limit raised to that power, provided that the answer is a real number and R and S are integers and S is not 0. So let's see how this applies algebraically. And we're going to start with a limit as x goes to c. So because x is going to c, what we can do is it looks like we've got a function plus a function minus a function, or actually a constant. So we can use our sum rule to break it up into 3 different limits, which we then evaluate. If we're going to evaluate the first one, we get to use our power rule, and we get c to the 4th plus 3c squared minus 8. More or less it looked like direct substitution, and that's what will happen for the first couple examples, direct substitution. Looking at example 2, we want to find the limit as x goes to 3 of this quotient, and so what we can do is we can take the limit as x goes to 3 of the numerator and the limit as x goes to 3 of the denominator. And if we substitute in, we get 3 squared minus 2 times 3 plus 1, which is 4, and then in the denominator we get 3 plus 1, which is 4. So our final limit as x goes to 3 of that function is 1. So far, direct substitution is working well for us, so let's move along. Here we're getting a little bit trickier. Example 3 asks us to find the left-hand limit, the right-hand limit, and the limit at the value of 2. So if we're taking the left-hand limit, that means we're approaching from the side where x is less than 2. So that would be this first equation. So we can take the limit there, and if we do direct substitution, we get a value of 5. If we're going to do the right-hand limit, we need to use the second equation because we're approaching from greater than 2. So we get to use the second equation, and direct substitution yields 1/3. And then the final part is asking us to evaluate what is the limit at 2, or as x goes to 2 for the function. Because these two values do not agree with one another, we say the limit does not exist. So in order for a limit to exist, the left-hand limit and the right-hand limit have to agree with one another. And as I've been saying all along, be careful, direct substitution does not always work, and the remaining examples are examples where direct substitution does not work. So let's take a look at example 4. In this case, if we did direct substitution, we'd wind up plugging these numbers in: 5 squared minus 6 times 5 plus 5 all over 5 squared minus 25, and it simplifies out to 0 over 0. Uh-oh, that's not allowed. The universe implodes when we divide by 0. So, the first and most common trick that we want to use is factoring. So we factor out the numerator, and if we factor the numerator, we get x minus 5 times x minus 1. And if we factor out the denominator, we get x minus 5 times x plus 5. And then we notice that the numerator and the denominator have a common term which cancels, and we now have a new limit to evaluate. And at this point, we can do direct substitution, and if we do, we get 4/10, which if we wanted to would simplify down to 2/5. So the limit as x approaches 5 of this quotient is 2/5. So moving on down, these are the 4 tricks that are most common when you're getting a divide by 0 error. The one I just demonstrated, which is factoring and canceling. In example 5, I'll talk about combining fractions so that you can cancel terms. In example 6, multiplying by the conjugate, which is probably a new term to you, or maybe a forgotten term. And the last one, this is a really special one that pops up pretty frequently on AP tests, is knowing that this limit is 1. And this is perhaps the hardest one to manipulate, but we should be really, really good at example 4. Example 5 we should be pretty good at, and example 6 we should be pretty good at. 7, that's the tricky one. There'll be one question on the AP test, more than likely, that requires you to remember that property. So let's take a look at these other examples.
Oh my! Oh, hooray!
Example 5. So if we do direct substitution in here, we would plug 2 into the equation, and we would get this spot right here where we have a 0 in the denominator, and that's not allowed, and so this won't work with direct substitution. So very often when I see lots of fractions, I think let's combine it into a single fraction. So what I'm going to do is, in the first step, I'm just going to write the function. Then I rewrite the function, and I'm finding the common denominator between the two pieces in the denominator. So we multiplied so that the two pieces had a common denominator. We combine those two pieces into a single fraction. So those two pieces combine into that. And then if we simplify the numerator, if we simplify that numerator, we get just x. And then we divide a fraction, so x divided by x over 2 times negative 2 plus x. And when we divide that, we multiply by the reciprocal, and those two x's cancel, and we wind up having that as being the same as that expression. And so now we can take the limit of that, and that gives us a direct substitution, which we can do, giving us a value of negative 2 for the answer. Alright, for example 6, this is the one where we're multiplying by the conjugate. And the thing that cues me off on these ones, very often, when I see a square root, or even more specifically, a square root minus or plus a number. So our numerator's got the square root, so my brain automatically jumps to, if direct substitution doesn't work, let's try the conjugate. So if I did direct substitution, I would get 2 minus 2 in the numerator over 4 minus 4 in the denominator, and that gives me a 0 over 0 error. So what I want to do is multiply by the conjugate. So what that means is I'm going to take my original equation and I'm going to multiply it by a value of 1. The way I decide what 1 to multiply it by is I put the same value on top and bottom, and the only difference is I change this minus 2 to a plus 2. So that's called the conjugate of the square root, or the numerator, the conjugate of the numerator. If I were to distribute by your foiling method, if that's what you want to call it, the numerator simplifies to x minus 4. I didn't distribute on the bottom because I like seeing that x minus 4 on the denominator. And if I cancel those two terms, I get 1 over root x plus 2. And that is another way to write my original equation. And that I can do direct substitution on. So I take the limit as x goes to 4 for that, and plug 4 in, direct substitution works. Root 4 is 2, 2 plus 2 is 4, so we get an answer of 1/4. Example 7 is perhaps the trickiest, so we'll talk about this in class and try to do a couple examples like this. But what clues me into this is whenever I see a trig function in a fraction that sometime and the limit is going to 0. That's what I look for when I try to use this rule. So the rule I'm calling on is that the limit as x goes to 0 of sine x over x is equal to 1. The only difference in here is we have sine of 3x. So if I want to make this look more like sine of x over x, what I could do is do a substitution. So if I let 3x equal u, now I have sine of u over 1/3 u. And I can pull the 1/3 out and get 3 sine u over u, which I then am able to take the limit of. And I apply that property right here. The limit as u goes to 0 of sine u over u is the same as that. So that's a value of 1, and I get 3 times 1. And there's my final answer. This is perhaps the simplest application of this rather complex limit, which we'll explore a couple more times as we progress through algebraic limits. There is a lot of possible ways to tackle this, so we'll work our way slowly through them. Alright, thank you for watching video 119, and the answer to the trivia question is the grooves carved into the side of a column. That is called fluting.